My presentation is about a picosecond opto-MTJ for non-volatile photonic memories. AOS means MTJ. My name is Luding. I'm a postdoc researcher at TU Eindhoven. This work was also supervised by Weisheng Zhao at Beihang University. The outline of my talk is as follows. I will start with a brief introduction of my research vision, ultrafast opto-MRAM. Then I will show some key experimental results, followed by the conclusion and outlook. In this post-Moore era, spintronic MRAM has been widely considered as an emerging non-volatile memory. Followed by its building block, magnetic signal junction, MRAM has launched commercial markets, being used as embedded memories in low-power consumption IoT devices. And leading semiconductor companies are also setting up ambitious research programs aiming at this technology. This is due to that the MRAM offers a best trade-off performance compared to other established non-volatile memories. So what is the bottleneck nowadays? So over the last 25 years, two generations of MRAM have been developed, classified by different operation schemes to write the free layer, based on external magnetic field or based on spin transfer torque. However, the switching speed is constrained by the underlying spin precession process in several nanoseconds, along with excessive energy consumption and incubation delay. So all these issues have remained a long-lasting challenge in the field of ultrafast spintronics. Very recently, single femtosecond laser-induced all-optical switching was observed in synthetic ferromagnetic gadolinium-cobalt system. It has been shown that the magnetization of this ferromagnetic bilayer could be fully switched at an ultrafast picosecond speed. Compared with other AOS alloys, this multi-layer system enables an easy tuning of interface-related phenomena, so it offers an ideal material platform for spintronic integration. We integrate AOS into the device level and develop an MRAM that could be fully operated by a femtosecond laser. This scientific question has become the main line of my research so far. As one of the first important steps towards such an ultra-fast opto-MRAM, in the last 5 years, we demonstrate the design, fabrication, and characterization of its basic memory bit cell, an opto-MTJ device, by integrating the two different concepts properly. Then I would like to introduce my experimental results briefly. Several design considerations have to be ensured simultaneously for an ideal opto free layer. A robust single-pulse AOS to enable an ultra-fast write, a high TMR ratio to achieve a high read margin, and a relatively high anisotropy to maintain a long-time data storage. A composite heterostructure is proposed, where the cobalt and the cobalt iron bond are coupled through an atom-thick tantalum spacer using the RKY interaction. So by using the two gadolinium cobalt interface and the cobalt iron bond and magnesium oxide interface. As shown from the power dependence measurement, a homogeneous domain is created by a single laser pulse with a very broad AOS writing window, so highly suitable to incorporate at the device level. After many repeated trials, we finally deposit the opto-MTJ full stack using magnetron sputtering, where the composite structure is used as a free layer. The indium tin oxide is used as the transparent top electrode. So the film exhibits the presence of strong PMA in both the free layer and the reference layer. According to the minor law, two parts of the free layer switch simultaneously due to the effective coupling through the atom-thick tantalum spacer. So this behavior is important to enable direct or optical writing. A symbolic logo is written on the stack using femtosecond laser, and BUAA stands for Beihang University, and TUE stands for Eindhoven University of Technology. As to the regions exposed by one pulse, a reverse domain is observed, but for the regions where two pulses overlapped, no net switch is observed, so confirming the single pulse AOS mechanism. The devices are fabricated at Beihang nano cleanroom with circular MTJ pillars. Optical microscopy shows that the device is in a very good shape, and the TMR loop it shows that the ratio is beyond 30% and could be further optimized. After fabrication, the device is characterized at Eindhoven University of Technology. So we observed that the TMR toggles between the AP and P state upon the incoming laser pulses. But with that said, the exact timescale of the switching is not clear yet. So how to further resolve such an ultra-fast femtosecond level magnetization dynamics? So a typical result based on time-resolved MOC measurement is shown here. So briefly, in the first several picosecond timescale, a rapid demagnetization is caused by the ultra-fast laser heating, and afterwards, magnetization reversal takes place within 10 picoseconds. And finally, a reverse magnetization orientation indicates it settled into a new thermal equilibrium. We observed that the picosecond speed is also preserved upon scaling down to 3 micrometer, as proved by the magnetization reversal within 5 picoseconds. As to the conclusion and outlook of my talk, based on the international joint effort from the two universities, we demonstrate an optically switchable MTJ device. Our group at TU Eindhoven is actively exploring along this research direction. By integrating two disciplines, namely spintronics and photonics, the ultimate vision is to enable a hybrid photonic memory device. My colleague Pingzhi Li will give a talk in another session from a different perspective by integrating ultra-fast AOS with racetrack and plasmonic structures. As to the outlook, future research trends include optimizing these hybrid devices and exploring possible roads towards a higher level of integration. And